Bret McGowen. I'm a developer advocate on the Google Cloud platform, and I'm based in the New York office. I'm going to be doing an overview talk of the Google Cloud platform. Has anyone seen our Cloud Spend demo here or heard about it? No? Okay, cool. I think this will be a kind of a fun, yes, I know, yeah, you've seen it in person. So it's going to be an introduction to the Google Cloud platform and a lot of the things we offer and kind of some of the technologies that are available. But it'll be kind of a fun walkthrough. We built a project to demonstrate it, and I'm going to walk you through what we built and all that. So, like I said, I'm based in the New York office, but I'm actually originally from Texas. That is my hat. How do you know if someone is from Texas? They tell you, exactly. So I have to. You can follow me there at BretMCG if you need to get a hold of me or with any questions. So, Cloud Spend is our demo that I mentioned, how we got all matrixy in the cloud. And Google's kind of a silly place. We do silly things. Our team is certainly no exception. And we wanted to talk about the Google Cloud platform in maybe an unusual way. I actually have a presentation that is a bunch of slides with bullet points that kind of goes through all the different things we have in cloud and talks about them in a very sort of slides-oriented manner. So if you guys prefer that, I can do that. But I think this will be a little bit more fun. So we actually decided, let's pretend that we're a startup, right? And we're going to build some cool or interesting project. And I'm going to walk you through how we built that and why we chose the technology that we did. And the kicker was, we came up with this idea for a series of conferences that we were putting on, but we only had 3 weeks to put it together. So in a way, it actually felt like a real startup because we had to haul butt to get this done. So what was our big idea? We thought, okay, we're going to pretend to be a startup because we want to show the power of the Google Cloud platform, and we need to get it to market very, very quickly. So what industry can we revolutionize in that short of a period of time? So we brainstormed, and we thought, and we came up, aha, you know what we're going to do? You guys know photo booths, right? Like they have them at weddings and malls and bar mitzvahs and things, and you get in there with like your friend. Okay, if you're like me, you get in there with your 10 friends and you cram in there and you're wearing like silly hats and scarves and Viking helmets and all this stuff, and you make crazy faces and it counts down like 3, 2, 1 and takes a picture, it takes a picture, it takes a picture, and it gives you a little printout at the end, right? So we're going to revolutionize that. So what if instead of a little printout, you got something that looks like this? All right, that would be pretty cool. Some kind of like floating in the air, frozen in time matrix looking thing. So this was our idea for our fake project to show off the power of the Google Cloud platform. So again, this is not a real project. This is not a real thing that is released by Google. It was built by Google as purely as a tech demo, so kind of a silly thing. So this is our engineering diagram. You can tell it's engineering because it has numbers and even like a radius. I was like, what? Wait, what circumference is what? So we had to get this sorted out. We sent this diagram to marketing. Marketing they tweaked it a little bit, and they sent it back. It looks pretty much the same, except there's no numbers at all, none whatsoever. So this is the engineering, marketing. So how does this work? So the idea is you have an arc of phones. The guy gets in the middle, or the gal gets in the middle, jumps up, and they all take a picture at the exact same time. So they all take a picture at slightly different angles at the exact same moment in time. We'll stitch it together in the cloud and create this rotating video. So sounds easy, right? It's not. And one of the reasons it's not is we wanted to use off-the-shelf components. So we wanted to do something that you could just buy in the store, right, without having to build some specialized hardware or do some like electrical engineering or any fancy wiring. We have 3 weeks, right? We got to pull this together quickly. And we wanted to use Android phones because we wanted to write software to do this. Any thoughts? So say you've got 20 phones in a row. Like, how do you get them all to take a picture at the exact same time? Any ideas? Suggestions? Yeah. All right. And so how do you have those apps know to take, like, what moment in time to take the photo? Any suggestions? Okay, so a timer. That's one thing. What we ran into there with that is even when they're all based on network time, they're all not exactly the same, right? There's like a close enough. And it turns out in order for that picture to be fairly smooth, it has to be within 20 milliseconds or so. So if this phone takes a picture now, and then this one over here takes one a second later, like you'll be in very different positions if you like jump up in the air. So a timer we worked with a little bit, but it's a little tricky. Any other? Oh, all right, we got so many suggestions, and we probably tried all of them. Yeah, so Bluetooth is one. Selfie sticks. We're going to come back to selfie sticks. Yeah. Right. So okay. So we ended up doing something pretty similar to that. So here's the issue. With Android specifically, you don't have a guaranteed response time for when you issue the command to take a photo. So Ray's here. Ray hates it when I put this video up. So I'm just going to leave it up while I explain this whole thing. So you guys just wait, watch it. Yeah. So the problem is, even if we can coordinate using like Bluetooth or something like that to take a picture at the exact same second of every phone, if to issue the command, this phone will take it at a slightly different time than this phone and this phone and this one, just on a hardware level. So burst mode was something we settled on. But then you still have the issue of, okay, so they all take, say, 60 photos. So there's going to be one frame from each camera that's the same. But now we have to figure out which frame is that. So we ended up using video, which is basically like burst mode, except, I jumped ahead, except we still need to find that one frame across all of them. So we chose audio, yes, sound. So there is, in the movies, you guys seen probably like, before they do and action, they have that like clapboard thing. So it's actually, it kind of was inspired by that. So we actually split an audio signal into the headset jack of every Android phone, and we play a beep. So it's completely silent on every video that each camera is taking, except for one beep. So then we'll upload each video to the cloud. The cloud looks for the frame that has that beep, extracts it, and then stitches it all together. So that's how I did. We had some trouble with this. If any of you guys have had like older Android mics that have headsets and also microphones, and then tried to use them in iPhone and vice versa, you realize like there's two different standards. So we had to get that sorted out. This is an extremely crude drawing that one of our coworkers did. Luckily at Google there's a lot of smart people, and we are not audio engineers or not electrical engineers. So we were like, help, how do we do this? And this is what came back. Ray showed this to me, and I was like, I don't know what to do with this. So I said, oh, okay, this looks like, no, I still don't know what to do with this. So we had a coworker, he put this together, the circuitry, ended up not working, so we had to use kind of some off-the-shelf, like literally these like Belkin, yeah. Mm-hmm. So that's what we'd like to do in a perfect world. The difference is it has to be at the like exact millisecond, basically. So like when you get that alert about whatever sad example you had of an abducted child, let's say there's a sale going on. When you get that, you're going to get that. Even if it's a second difference, it feels the same to you and I, but it has to be like the exact like millisecond, basically. So just the timing of traffic through the internet or Bluetooth, or even like I said, just the camera response time in Android, like is not fast enough to guarantee the same frame is taken at the same second or the same moment in time. So that's how we came up with audio. And actually, talking to some colleagues, and we've toured this rig. I don't have it set up, the Cloudspin demo here, but we've taken it to a few different conferences and talking to people. It turns out we accidentally discovered like a pretty common way that people do this, which is audio. It's easy, it's understood, it's off the shelf. You can go to like Best Buy and buy a lot of these components, which is what we did. We went and we bought like audio splitters and just like headset phones and adapters from like AV shops to get this working. And this is our off-the-shelf thing. Basically, we have a tablet here. Like we press a button, and it makes a beep. It goes beep. And then goes into an amplifier, and then splits it 5 ways, 4 times to go to 20 different phones. And those are like go into their headset jack. So here is one video. This is of our coworker, Robert. And if I have audio, let me play this. Oops. So that kind of horrible sounding beep is the marker. So that is me pressing the button on the tablet. And it pulls one frame, and then every camera does it, and it takes all these frames, and it stitches it together. So That was kind of the Android side. That was the hardware side. But I'm here to talk about cloud. So yeah. So yes, actually that would work. Like in our very first prototypes, we had like a little room dedicated that we were putting this together, and I would just jump up and go like, "Ha!" or whatever, and it worked. It worked totally fine. But since we're taking these to different conferences and things, some of them are super loud. Like they're playing music in the hallways. There's like people talking next to the cameras, and so for you to consistently be loud enough, it has to be much louder than the surrounding thing to get like a good clean like this frame. But if you have a quiet enough environment, yeah, absolutely. And as kind of our backup plan, that's what we would do, is we'd be like, we would just yell if we had to. Luckily, it's worked with audio cables, but yeah, it's the exact same idea. Yes. So we thought about that, but it turns out that computer vision is hard, so we didn't. No, but since then, I've actually we've talked to quite a few computer vision specialists, and you know, if in that great and glorious day when I get so much free time, I'm totally going to look into it, because it's possible. Because you could basically look at like what in every set of frames, like what has the highest movement essentially, right? And that's probably like the peak of their arc. It has a few side effects because not everyone jumps. So some people like pose like this, or like we have a guy, a break dancer, so he's like going down. So like it's not always that, but yeah, that's totally like an option. You're talking about like using like the movement of the visual, or mm-hmm. So possibly. Probably how you would do that, you run into a little bit the timestamp problem, which says that like 3:01:01:01 to that phone is not necessarily 3:01:01:01 to this phone. It may be 3:01:05. And 99.999% of the time, like, you would never ever notice that difference. But something like this, you do notice the difference. There are some things you can do. We thought about setting like a local NTP server, so each phone could talk super quickly on the local network and say like, hey, the NTP server thinks it's this time, I think it's this time, therefore I know that I'm 17 milliseconds faster than NTP server, and like I'll report that, and then the cloud algorithm can adjust accordingly. So it is possible probably to solve that, but like I said, we had 3 weeks, and so this is what we arrived at. So it is possible maybe to do something like that with timestamps. I think we had another cloud. Yes. All right. Let's get into the cloud stuff. So this is our cloud architecture. So here we have our devices, which are Android phones, and each one of those is going to upload a short video, like I talked about, to some kind of storage mechanism. And then that storage bucket is going to notify someone, hey, I have a video for you to process. The notification processor puts it into a queue, an extraction queue. The extractors pick it up, pulls out one frame from each video. It's going to send it to a stitching queue, and then the stitcher is then going to stitch those frames into one final video. So that's a super quick version of the cloud architecture, and then we'll get into some more detail as we go along. So first question, how do we coordinate 19 cameras? So this is not necessarily how do we tell them all to take a photo at the exact same time, but there's a lot of general coordination we need to do. So it's tricky. There's a lot to do in like a very, very short period of time, like literally, not like real time, but basically real time. So what am I talking about coordination? So there are things like status, like am I in an error state of some kind, like I have crashed, or so if we have microphones, so like someone has unplugged the microphone. So there are things we need to know, like in our coordinating tablet, like we need to know basically immediately, oh, whoops, camera 17 died, we need to go fix it. We need to set the shutter speed and ISO and those sort of things. So again, we're going to different conference venues that have very different lighting situations. So some are very dark. We were in Amsterdam. It's basically we're in a cave. It was so dark in there. And then we were in London, and it's like almost outside, and it's like so bright. So we don't want to have to like recompile our APK and redeploy to every phone and be like, whoops, nope, that wasn't it. Let's try it again. Let's try it again. So we want to be able to put it in somewhere and then pretty much instantly change these settings on all these phones. And then we do want a vague timestamp. So even though we're taking video, like we need to know when do you start taking video and when you stop taking video. So to do this, we chose Firebase, which there's actually a session going on, I think right now, about Firebase. I encourage you to check it out. Martin Omander from Google is doing another talk about it tomorrow at I think 11:45. I'd encourage you to check it out. It's a really great technology. Has anyone used Firebase or is familiar with it? Yeah. So it does a lot. One of the things that it does that we used it for is essentially is a database that does real-time synchronization. So what that means is I write a value to Firebase. For example, I'll show you in the next slide. But for example, a timestamp of like be recording a video at this time. And then automatically Firebase will tell every subscriber within milliseconds this new value. So it's still not fast enough for us to coordinate the actual taking of the photos, but it is very fast for us to tell it things like, I'm in an error state, and instantly everybody else knows that this camera has had an error, or I finished recording, or here's the time you need to be recording. So that happens very, very quickly. So we use Firebase for that. Yeah, so it's a JSON NoSQL database with real-time sync, basically for free. And what's nice is, again, we have 3 weeks, so we have to move very, very quickly. We could write all this code on our Android phones because Firebase is what we kind of unofficially call backend as a service, which means you've got this very, very powerful database synchronization platform called Firebase that you have to write basically no code to do. You just set it up, and you can write all of your code in Android or iOS or web. So Firebase supports all of those, and then updates very, very quickly. And it's easy. So here's an example of some code on the Android side. We just do camera status. Does this have a little green glowing thing? Yes, but it doesn't show up. So basically, you have this camera status. It's just a plain old Java object. You set the properties, and then you say camera status ref, which is a Firebase reference, set value, and you give it that object. And then automatically, it saves it to Firebase and pushes it out within milliseconds to everybody else to say, here's my status, which is hopefully not broken. And here is an example of our control app. So these are all green. And then they'll have like a version, and they all say external mic. So again, if someone unplugged the mic, we would know, basically immediately, we would know on this tablet. And over on the right is like a visualization of some of the data in Firebase. So I'll hit start countdown, and it has 8, so it's an 8-second countdown. So it'll add 8 seconds to the current time, and then it'll write it over here in this timestamp value. And then again, within milliseconds, every phone in that circle, in that semicircle, will get this value. And it'll know, aha, I'm gonna start recording video at that time. All right, so once we have started recording the video, we needed to upload it somewhere. So we took a look at some of the different technologies. Here's our requirements. It needs to have a large amount of unstructured data. We need immediate access. So in our sort of fake photo booth world, like once we upload the video, we need to be able to read it immediately. If there's some family in a mall and the little kid wants their photo like now, like we can't wait. Well, please wait while your data propagates across our global data center network, right? Like no, we need to upload it and work on it immediately. So that's definitely a requirement. And we also want notifications for all newly arrived objects. I'll talk about this in a second. So we chose Google Cloud Storage, which is our like blob storage offering. So this is basically binary data, right? Cat videos. Here are some options, just super quickly. Standard storage is over on the left, and then something I think is very interesting is Nearline over on the right. You can notice it's much, much cheaper and not that much slower. This is kind of our archival offering. So this would be like long-term storage. But to give you a sense of how slow is in this bar graph, like we're talking seconds to maybe a minute. So that's actually really fast for your long-term like archival storage. And these all use the same API, so you don't have to change much code. All right, so here is our API call from New York, where Ray and I are building our Android phones, to Francesc, who's actually doing a Go Code Lab next door. We're rarely in the same place. So here is what this API call looked like. Yes, I got on the telephone and I called Francesc and I said, hey, the files are ready for you. Please process them. And I'm only kind of joking because cloud storage lets you do something called object change notification. And what that is you register with your storage input bucket itself. You say, hey, every time I upload a file, I delete a file, I modify a file, call some API for me. And that's nice because on the Android side, when we were working on this, if he changes where his API lives, or he writes it in PHP now instead of Go, which he would never do because he loves Go, but I don't have to know about it. All I need to know on the Android side is I upload my file and I'm done. And the storage mechanism actually will take care of it. So we have an SDK utility called GSUtil. So we just register this endpoint. And what that needs to be, it's just some kind of HTTPS endpoint. And we just register it with the storage mechanism. So all the client does, which is the Android phone, uploads the video, and then actually our storage mechanism calls the next step in the chain, calls the API for us. And it's just a JSON payload. It has like, here's what the file is, here's the MIME type, that kind of a thing. So that's really nice because Francesca and I didn't have to discuss API design at all. Like my Android phone just uploads the file and I just moved on. Here is the Android code to upload the file. I don't think there's anything like super noteworthy about this, other than to say it's just, right, so I'm setting my MIME type, which is video MP4, and this is essentially all the code that was necessary to upload it to Google Cloud Storage. Edge caching. So we didn't use this in our demo, but it's kind of a cool feature of Google Cloud Storage, which is that as users start to request files, if they're public, we'll automatically start moving them out geographically to regions that users are closest to. It's not a guarantee, but it is kind of a neat feature. And so you can imagine maybe in our photo booth world, like we start to add some social component, and people are sharing these videos all around the world, like it will automatically start caching those in data centers that are close to our users. All right, notification processing. So this is the next step in the chain. This is the step that I've uploaded a video, and we have to tell someone, I have a video, please like do something. So what are our requirements here? It needs to be able to handle an HTTPS post request, because that is what our cloud storage mechanism will call as the next step in the chain. We want simple authorization, or authentication rather. We have 3 weeks, we don't have time to muck with it. And that it also needs to, all it needs to do is process tasks and put them in a queue, so nothing too complicated. So we chose App Engine. Has anyone used App Engine? Are you familiar with it? Okay, so App Engine is, it's a pretty popular product on Google Cloud Platform. And the idea is you take your code, you upload it to the cloud, and it just runs, right? So a lot of us live in sort of this virtual server world where we need to provision, okay, so we're processing these videos. You know, we need to provision 25 video processing virtual machines. They need to all run Ubuntu. They need to all have such and such version of ImageMagick and of FFmpeg, and they need to have such and such version of Ubuntu, and we need to make sure that we install the security updates. And if we get more traffic, we don't need 15 anymore. We actually need 75. But now we have 75 that are sitting overnight. We have to pay for them, so we have to turn them off, blah, 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 blah. So the goal of App Engine is to not have to worry about any of that. You just take your code, like we love to write code, you just put it into App Engine and it runs. And within some limitations, that's what it does. So it scales automatically, which is really big. So if you have no traffic, it scales down to very small or maybe 0. And then if you have tons and tons of traffic, it automatically scales up to meet that. And you don't have to do anything. Like that is the beauty of App Engine. It scales up for you. You don't have to worry about patches or updates to the operating system. Google takes care of that for you. And then monitoring it as well. Like we have site reliability engineers that are watching App Engine all the time to make sure that if it goes down or has issues, like they're fixing it 24/7. It supports PHP, Java, Go, Python, and Node.js as well. So it's pretty nice. What else do I want to say about that? You can do A/B testing, local test environment. It's cool. So I encourage you to check out App Engine. We actually have a 28-hour-a-day free tier, which, despite what your bosses may think, you don't have 28 hours in a day. So why 28? And that's because that's just the number of compute hours, right? So if you could have, like, for example, 4 hours a day, where it sort of bursts to two machines to handle your application, and that's still free. So that's cool. All right, messaging. So say Cloud Spin gets popular, like super popular. So say Austin, Texas, South by Southwest, we're setting this up at a music festival, and this dude is rocking this sweet air guitar, and there's tons of these set up. And then maybe in Amsterdam, there's some martial arts expo, Kids are doing this, and then people are using this for team building exercises all the way around the world in Japan. This is all happening all at once, and we did not expect it because someone wrote about it in CNN. And crap, now all these like kind of mildly popular things that we've set up around the world are getting hammered. And now instead of getting 100 videos an hour, we're getting 10,000 videos an hour. Well, if we just kept our cloud resources static and the same level, like we would start to drop those, right? We would start to lose messages and lose requests for video processing. So we need to sort of buffer those. So we're like, whoa, hold on. Like, I maybe not am ready to do anything with this video yet, but I at least want to buffer this message. So we want to put in a message queue of some kind as like a shock absorber. So even if we aren't actually processing these videos yet, we want to at least put this in a queue so that somebody else can pick it up and work as soon as we can scale up to the additional compute power. So for this, we used pull subscription. Let me talk about this real quick. So the difference between push and pull subscription. So a push subscription is I'm sort of the message queue. I have a new message, and I'm going to tell every subscriber, hey, here's a new message. Like, please do something with this. So that's what that is. We want a pull subscription, which is the opposite, which is I'm a subscriber, and I am now ready to handle something, so I'm going to ask the messaging queue, like, please give me the latest message so I can work on it. I'll work on it. I say I'm done, and then I'll ask for the next one. So the reason we want this is twofold. One, we don't want to tell every subscriber that we have a new video. And then two, it makes scaling our instances very easy because we don't have to register. Every time we spin up a new instance of an image processor, we don't have to tell the messaging queue, like, oh, hey, I just added 10 image processors. They can just stand up, and whenever they're ready, they'll just ask on their own for the next message, and that message being a video, some data about a video to process. So there's an ACK here too, which is in both of these models, which is just the image processor saying, like, I have completed working on this message. Consider this message handled. So if something happens and your image processor goes down and it dies, and it doesn't send that ACK, then the message queue will assume that it died, and then it'll give it out to someone else. So it's a really nice and easy way to build a lot of robustness into your app. So we use a product called Cloud PubSub, which we're using in sort of this way. It's kind of it is a publisher subscriber tool. Let's see. All right, here's an example of some architectures. I won't like really walk through this, but you can kind of get the gist of it. So we've got publishers, which in this case would be our App Engine app that says, I'm going to publish a message that's saying, I have a video for you to process. And then it could publish to various topics. So we would just have a topic that says extract, for example, extract a frame. And then you can set up subscriptions, which then give messages to subscribers. And you can have any crazy combination of publishers to subscribers that you want. So all the way from one publisher publishing out to a ton of subscribers, like in a fan-out model, or a ton of publishers publishing to one subscriber or anything in between. And subscribers can be anything that can do an HTTPS post to googleapis.com. So that could be an Android app, an iOS app, it could be an App Engine app, it could be a Compute Engine app, it could be your desktop browser. There's a whole bunch of things. So it's good. We can use anything we want. Email, like not directly. So it has to be able to do an HTTPS post. So you could probably have a service that is checking like your email account, and then it could do an HTTPS post to publish. Yeah. So for example, in ours, we have our App Engine notification processor post a topic, post a message to the extract topic, and the extractors are subscribed, and they know. So the extractors here, I'll talk about them in a second, are the ones that are pulling one frame out of a video. So they're just listening for this. Right. So at this point, we're feeling really good about our cloud architecture, but we don't have the hardware all set up yet. And so it's time to put that all together. So we actually had a little room, not in the main Google office in New York. It was at some other building that no one even knew like belonged to Google. So it felt kind of like we were a legitimate secret startup. But before we spent a lot of money on phones and tripods and whatever, like we needed to know that this would work. And we had a pretty good idea that it would, but we didn't know for sure yet. So we had to quickly and cheaply find out. So here is us trying to find out what the right distance is from a camera to the person. And we didn't have any measuring tape, but for some reason Ray had police caution tape, crime scene tape. I don't know why, but we use that. So we use this caution tape to measure the distance. In case you're interested, the ideal distance between the person in the center and the camera is 8 cautions. So yeah. That's very rough measurement. That's a unit of measurement I was not familiar with. So we didn't have measuring tape, and we didn't have like sort of mounts or tripods for our phones, so we actually had to use selfie sticks. And I don't know if you've ever tried to use a selfie stick as a tripod, but it's literally the least stable thing you can use to hold up your phone. Like, I would roll by on my office chair, and then just me blowing by, just the wind would start to topple this, and I'd have to like jump on the ground and like catch this $500 phone before it smashed on the floor, and I had to explain to my boss like why I spent so much money putting the thing on top of a selfie stick. So needless to say, we eventually felt confident enough to actually move away from selfie sticks. We bought this whole arc of tripods. We set it up in our studio. This is our other room down in the Google building. And they have real mounts and real tripods, which is good. And we even bought some lights. So this is our intern, Matt. Matt is a very smart guy. In fact, our image extraction algorithm, he wrote the very first version. So he's super smart. But he could not figure out how to turn this light on. It's just some light we bought on Amazon. I don't know if you can tell in this screen, but that's the plug right there. Oh, Matt. So yeah, we had a good time. All right, so anyway, back to the cloud. So pipeline processing. This is the code that actually is doing the processing of the video. It's finding a frame, it's pulling it out, and it's sticking them all together. So from a cloud perspective, like what is that running on? What technologies are we using? All right, a little bit about what the algorithm is. So this is an audio track of one of the videos, and you can see sort of the intensity of the audio signal and then the corresponding frame. So it's looking for the one beep that's 4 times louder than the rest of the audio track. Can anyone see where this frame might be? Yes, 70, yeah, exactly. So this is what the algorithm is doing. It's basically just looking at this audio track and finding something that's bigger. So we're using a third-party, just a Python library called MoviePy. I'm not going to walk through the code, but the short version is it's finding the average volume of the frame, and it's finding the first frame it can find that's at least 4 times louder than the average of the rest of it. So that's why it was hard to just use ambient noise, because like if people are talking and yelling and there's music, then this graph starts to look much more uneven, and you might accidentally get something that's 4 times louder up here when really like that's the beep. And then maybe it's this frame for some cameras and not for others. So, all right. It needs to run for a long time because we're going to have this thing up and running all the time, and it needs to be able to get messages from our pub sub. So we used Compute Engine, which I may have mentioned a little bit briefly. So this is our virtual machine offering, right? This is if I want to specify, I don't want the App Engine experience of just upload my code and move on with my life. Like I actually have some specialized process that I want to define, like how many cores I want on my CPU. I want this much, I want 10 terabytes of local SSD, or I want 208 gigs of RAM. Like if I want to specify all that, then App Engine is what I would use. So we have zones in Europe, the US, and Asia, and they provision very quickly. So that's part of why we wanted to use it for this part. So this part that we're running on the extractor, where it's finding that one frame, we wanted to be able to scale that up very, very quickly if necessary. So again, in the scenario where CNN or TechCrunch or something is writing about our fake startup, and we just get massive traffic quickly, we need to be able to spin up very, very quickly. And Compute Engine can do that. I think this is impressive. It certainly blew my socks off when I heard this, but you could spin up potentially like 1,000 virtual machines in like 2 to 3 minutes. So that's really fast. That's really fast provisioning. And it's consistently performant too. So with a lot of cloud providers, like if you have what we call noisy neighbors, which is like on your physical host machine, some virtual machines are just churning away because some guy's got like some ridiculous process that's like burning through all the CPU. It can start to affect you. But with Google Compute Engine, it doesn't. Like we keep that performance very, very consistent. And it also allows us to do autoscaling. So I talked about all these requests for image extraction coming into our message queue. We can actually auto-scale to the size of that queue. So we could say, if all of a sudden we have 1,000 videos come in, we actually want to scale up to 1,000 virtual machines. So we get one image processor for every video that's there. It would be a little overkill, but we could do that. And it would look at that queue, and it would say, we have 1,000 incoming requests, scale up to 1,000. When that queue size starts to go down, our autoscaler will start to scale the number of virtual machines down. And it's essentially, you just define a recipe for a virtual machine. You say, it looks like this operating system, this much RAM, this much CPU, and then I want to install this software through some startup script. And it just automatically takes care of provisioning those. All right, so we also put it into containers. Was anyone in the Kubernetes code lab earlier? All right, so I'm going to very, very quickly, we're starting to run short on time, very quickly kind of talk about what containers are. So containers are, if here's your app engine experience in the bottom right, which is very efficient. Like you spend almost all of your time just writing code and not worrying about any infrastructure whatsoever. Versus a compute engine where you do have to worry about infrastructure. So it gives you the most flexibility, but you have to worry about infrastructure. Again, it's a virtual machine that you have to manage, but it's still a machine you have to manage. You have to install security patches and OS updates, and you have to make sure that they don't get out of sync, or like, whoops, I installed updates to this machine, but not to this machine. I upgraded to version 3.1 here, but 3.01 here, right? So if only there was something that was like maximum flexibility and maximum efficiency. Incidentally, I don't know what is this square where it's not at all flexible and not at all efficient, but I'm pretty sure we used it at my last job. So container engine. Let me talk a little bit about what containers are. So back in the olden days of, let's say, 2000, when I had my startup and Ray had his startup, and we were like literally putting these on machines like under our desks or in our closets, right? This is, all of our apps were on one machine, but that kind of sucks because they have shared libraries and they start to step on each other. Like, I need this version of Python, he needs this version. I upgrade it so that this app has the new version, but the old app doesn't want the new version, right? Like, that sucks. So we moved to virtual machines, where it's essentially this virtual machine for this app, but it's still a little overkill because you have a whole virtual machine for like one app, right? Like, that seems very inefficient. So we went from, this is the old one, shared libraries and shared kernel, to no shared libraries and no shared kernels. So containers kind of take the operating system kernel like out of it. So it's just your app and its libraries that are packaged together. And Docker is a container format that you may have heard of. Docker is a third-party company. It's not a Google company. But they have like a very popular defined container format that is sort of the de facto standard these days. And it's nice because you can also declaratively package your app with your code with your operating system. So you can say, my guestbook app needs this version of Python on this version of Ubuntu with these installed libraries. And it's defined declaratively. So when you spin up new instances of your app, like, it's just going to look at this sort of recipe, and it's going to know exactly how to build an image of what you want. And so you don't have to worry about things getting out of sync. So that's very useful. What else? Yeah, this is kind of just explaining that. So at the bottom, you say, I've got a Debian image. These are the libraries. I'm running PHP and Apache, and then your app code sits on top. One other thing that's kind of nice about Docker is there's a repository called Docker Hub. So there's a ton of these like pre-created container images out there for you. So if I want a MySQL that's just ready to go, I can just point it to a MySQL Docker image on Docker Hub, put my app on top of it, package it up, and I can easily deploy it. And container engine is, just real quickly, is a way of orchestrating all this. So I can package up all my operating system and app code, but I still need a way to know, like, I need 5 web heads, I need 3 database instances, I need 20 Memcache instances. So Container Engine runs an open source project called Kubernetes that essentially lets you define that. And it'll take care of monitoring your app to know if I want 3 like web servers and one goes down, it'll instantly spin back up another one. So that's what that is. We did not do this in Cloud Spin. We're not using Container Engine, but we could, and we probably should. All right, so we're almost to the finished video. We've extracted all these frames, and each extractor, when it's done, it puts a stitcher request into the stitcher queue. But we haven't had a stitcher actually put it together into a final video. So to do that, we need a little coordination. And the reason we need to do that is because when the Stitcher gets a request to stitch everything together. It gets that request after every frame is done. So if frame 1 is done, it'll say, okay, Stitcher, go. But you only have one frame. And then it can't just wait until, say, frame 20 is done, because they're all asynchronous, right? We've got all these virtual machines working in parallel, extracting all these frames. So maybe frame 7 is done, and then frame 10 is done, and then frame 3 is done, and then frame 20 is done. So at that point, though, 20 is done, but we still have a whole bunch of missing frames. So we need some kind of database to say, like, frame 1 is done, frame 2 is done, and store that somewhere. So when the Stitcher gets a request, it can look at the database and say, are frames 1 through 20 done? And when that is true, then it can actually read from the database, yes, we have all the frames, going to go to the temporary storage, pick out the frames that we've extracted, and stitch them together. And for that, we also use Firebase. This also gives us a nice advantage because Firebase is real-time synchronization. We built a visualizer, so you can see in sort of real time, like the photo getting taken from the Android, the frame getting extracted, and then it getting stitched together. And I will show you what this all looks like, the great and glorious cloud spin. I thought about having some colleagues, back in New York, like set this up and doing a remote demo, but no one wants to do a demo, much less a remote live demo from another state. So next best thing is a recorded video. All right, we do not actually want to hear the audio on this. So this is what our rig looked like. You can see it's kind of this metal arc of phones with these mounts. And then here's Robert awkwardly pointing at the tablet. You can see all the screens go yellow. That means they're ready to start, or they're getting ready to start recording. And when they are ready, they're going to turn blue. So they all turn blue. Now Ray's going to jump, and the Robert's going to hit play or hit beep on the tablet, and it put a beep and marked it in the frame. Now Ray's going to do his best Vanna White impression and point our visualizer out. So, all right, so here's the visualizer I was talking about. So as it's going through the process and each frame is updating its status in Firebase, we can tell within milliseconds this web visualizer is getting updated. So the gray means uploading, and then the green means processing. So as it goes through this, you can see it's found that frame, found that frame, found that frame. And then once it finds all the frames, then it will stitch them together. And thanks to the power of time-lapse photography, we are going to jump ahead to where there's only one left, and then dun, da, da, da. There we go. It stitches them together. Woohoo! All right. Yes. Thank you. Pressing play is a much more satisfying way to do a demo. All right, so real quickly, just to walk through the cloud tech that we use for this demo. Firebase, to coordinate all the Android phones. They all upload to Google Cloud Storage as the input bucket. They tell App Engine on the notification processor, who then puts that message into a queue in Cloud PubSub. Cloud PubSub then gets its message consumed by our extractors, which are running on Compute Engine, and coordinated with Firebase to create this final image. So demo builders, myself, Francesc, who's next door, Ray, who's over here, Kathy was in Seattle. I tried to Photoshop myself in this animated GIF, but it was really hard. So don't feel bad, though, that I wasn't in this frame. I was in Mexico on a beach, so it was fine. I told them, like, you guys let me know how it turned out. All right, we have probably not enough time. Does anyone want to see something about BigQuery for like 3 minutes? Yes, all right. You guys had too much interesting things to say about our Android synchronization. So, all right, so I guess some people have heard of BigQuery. It is our massive data analysis database, and massive, like being on the order of terabytes. So it uses, and Ray talked a little bit about this in his overview talk earlier today, it uses a SQL-like syntax. So you can essentially write SQL queries that perform very, very quickly over massive data sets. So blah, 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 I know you just want to see a demo, so let's do that. I'm going to pull up. All right, so what is the most productive day of the week for Wikipedia contributors? So that is the question of the day. So we have kind of these public data sets in BigQuery that you can go and play around with for free just to kind of get a sense of like the power of it, right? So one of the data sets we have for Wikipedia is a history of years, like I think a decade or something, of all the edit records that has ever gone into it. So anytime anyone edited something in Wikipedia is essentially the database that we're querying. So just to give you a sense of what the data looks like, Let me move this up a little bit. So here's the edit record. Here's like the title, the ID. I don't know what any of this stuff is really. Username, timestamp, blah, blah, blah. So let's query something. Let's find out, what was our question? What was the most, like the day of the week where like the most edits are done? Let me grab this query. This is bonus material because it has nothing to do with Cloud Spin, but it is a cool part of our cloud product, Google Cloud Platform. All right, so select day of week, which is just translating a timestamp into like 1, 2, 3, 4, 5, 6, 7, where 1 is Monday and 7 is Sunday. And then it's going to say how many edits happened on that day from Wikipedia. All right, so show options. We will not use cache results. This way we can see how long it takes to do with using no caching whatsoever. So 2 second, well, okay, all right. So for that particular one, 2.3 gigs processed in 2.1 seconds. And that's pretty fast. Like that's quite fast. And what's also interesting about that is there's no indices or indexes set up on this database at all. Like literally it's just dumped and that's it. You don't have to set up any indexes. So that's pretty cool. 2.3 gigs in 2.1 seconds is quite fast. But I feel like we could probably do something a little more impressive. So let's take this. If I can scroll down. I will run this, and then that will be it. All right, let's compose query. Did I click it? Come on. This web interface does not run a BigQuery. It's faster than that, I promise. There we go. All right, so what we're doing is we're going to take all of the hits, essentially, that have come in to Wikipedia in, I don't know, what is this? May through December of 2014, and for some reason 2 months in 2015. So every single hit that came into Wikipedia, like every page hit, it's going to just sum them up and see how many there were. And we'll take off cached results. And let's run this. So can you guys see that? Like query running, 4.5 seconds, 6, 7, 8. It's like a reverse countdown. All right. So 11.2 seconds, 422 gigabytes processed. That is really fast. And in case you're curious, how many that is, let's see, 446 billion hits to Wikipedia. So 11 seconds, that's pretty good, right? I mean, I feel like, yes. And this just came out, the very last thing, this came out, I think, 2 weeks ago or something. You can now do user-defined functions in BigQuery. So you can kind of do your own like sort of analysis as part of this query and get this kind of speed and performance. So very cool. That is all I had. If you have any questions, come and find me. Or Ray is up here as well. And thank you for your time. Thanks.